Welcome to Ask and Learn.
The free body diagram for the mass going straight up would of course be force normal. Going straight down would be mg, gravitational force. At an angle here, defined theta, we have the tension from the rope, and then opposite to the direction of motion, the frictional force. After drawing the free body diagram, we can then apply the Newton's second law in the x and y directions. So T, the tension cosine of theta, minus the frictional force would be equaling 0. This is the system at constant velocity, and we can say that T sine of theta plus the force normal minus the gravitational force mg, this will equal 0. And we know that theta in this case is equaling 15 degrees. We can say that here the first equation gives that the frictional force would be equaling to T cosine of theta. And the second gives that the force normal is going to be equaling to the gravitational force mg minus T sine of theta. And we know that if the two remain at rest, this means that the frictional force must be less than the coefficient of static friction multiplied by the force normal. Or we can say that T cosine of theta must be less than the coefficient of static friction, and then substituting it for the force normal, mg minus T sine of theta. We can solve for, we can say when the tension force is sufficient to just the crate moving, so just in order to start the crate for moving, just exceeding that maximum static frictional force, we can say that T cosine of theta will be equaling to the coefficient of static friction, mg, minus T sine of theta. And for part A, we can solve for the tension. The tension T would then be equaling the coefficient of static friction times the gravitational force divided by cosine of theta plus the coefficient of static friction multiplied by sine of theta. We can solve. This would be 0.50 multiplied by 68 kilograms multiplied by 9.8 meters per second squared. This is going to be divided by cosine of 15 degrees plus 0.50 multiplied by sine of 15 degrees. And we find that the tension force T is going to be equaling to approximately 304 newtons. So that'd be your answer for part A. For part B, we can say that rewriting Newton's second law for crate. So now applying Newton's second law in the x direction, T cosine of theta minus the frictional force will equal the mass times the acceleration of the system. And then we have T sine of theta plus the force normal minus mg equaling again 0. So in the y direction, of course, we have translational equilibrium. However, in the x direction, of course, we have moving at a certain x direction. Now we have that the friction is equaling the coefficient of kinetic friction multiplied by the force normal. And the force normal is now equaling mg minus T sine of theta. And we can then say that the frictional force would be equaling to the coefficient of kinetic friction multiplied by mg minus T sine of theta. So we can substitute this expression into the first equation here, and we can say that then T cosine of theta minus the coefficient of kinetic friction multiplied by mg minus T sine of theta. This is going to be equaling to the mass times the acceleration of the crate. And so the acceleration of the crate for part B would be equaling T multiplied by cosine of theta plus the coefficient of kinetic friction multiplied by sine of theta. This would be divided by the mass minus the coefficient of kinetic friction multiplied by the acceleration due to gravity. We can substitute and solve 304 newtons multiplied by cosine of 15 degrees plus 0.35 multiplied by sine of 15 degrees divided by the mass of 68 kilograms minus 0.35 multiplied by 9.8 meters per second squared. And we find that the acceleration A is then going to be equaling to approximately 1.3 meters per second squared. This would be our final answer for part B. The solution, thank you.